Swayam Prabha. Digital India. Educated India.
Very good morning, good evening, good afternoon to all my dear friends. I am Raghunandan Sengupta from the IME department, IIT Kanpur, and this is the TQM course 1, and I did mention in my last lecture. So we will have the TQM 2 also. So this is the 17th lecture, which would be the second lecture in the 4th week, because as you remember, there are 5 lectures per week. So we would already, when it's the 15th one, you have already completed your 3 weeks. So continuing with the OC curves, the concept of AQL, concept of LTPD, concept of capital N, small n, C, and how the curves would change, and how the shape and the characteristics of the curves would change depending on capital N, small n, C, and also the distributions. We did understand few of the fundamental things. So what we are interested to study now is basically the average outgoing quality, which is AOQ. So that the average number of lots depending on the percentage and unexpected lots would be. So now in the lot you have, technically the population is not infinite, which is capital N. So when you are trying to find out the average outgoing quality, so consider you have picked up small n. So what we would have in front of us is basically we have a so-called lot which is of size, one is n, small n, and one is basically capital N my small n. So the number of defects depending on small n would also have a consequence on the number of so-called defects and acceptance on the other lot, which is capital N my small n. So we want to find out basically the multiplication of these following factors, which are, listen to me carefully, is the probability of accepting a lot. So you either accept or reject the lot would basically be dictated by P suffix A or AC, and the fraction of the defects depending on what is the overall probability which is there would be given by the value of P, and the lot size which I mentioned, the total size is capital N and the sample size is basically small n. So if you are basically considering these values, so it would be capital N minus small n divided by n would give you the relative frequency, that should be multiplied by P, which is basically fraction of defective, and obviously that would also be multiplied by the factor of P suffix AC, which is the probability of accepting the lot, based on which you can find out the value of AOQ, which is the average outgoing quality. Now average outgoing quality limit, so obviously these values would keep increasing, but obviously they would have a particular optimum value, some star value of AOQ star, after which you should basically decrease. But that increase and decrease would be dictated by, as if you remember, by 4 actual set of informations. One is P suffix AC, one is P as I mentioned, the other would be basically the lot size, and one would be the sample size. So if you basically are able to plot the actual AOQ of any set of informations, it will basically be a distribution as shown in this figure. So let me highlight it. So this is the distribution which you have. Technically this is a smooth line if you have number of points is infinite, and there would be some point at the highest level which would be given by the average approximate AOQ value, which is the highest value, depending on which you can find out the maximum level of AOQ. So obviously that will change from example to example, it will change depending on whatever distribution you have, it will change on the value of capital N, it will change on the value of small n, it will change on the value of P suffix AC, it will change on the value of P, and all these things. So in this example, as the incoming fraction defective P's are measured along the x-axis, and the fraction defective out, which is the value which you are measuring along the y-axis, obviously there would be a peak after which it will start decreasing, and that optimum value we have to find out in order to understand that what is the threshold value based on which we can take a decision for that particular lot, for that particular distribution, for that particular small n value, for that particular capital N value. So, average total inspection obviously will have some cost. So, I will come to the cost very briefly later on. So, average total inspection, which is ATI. So, if the lots contains no defects, no lots will be rejected, and the amount of inspection would be per lot, which will be given by the cost of inspection each item multiplied by the overall sample size. So, it will be, as I am mentioning, I will read it again, and the amount of inspection will per lot be the sample size n multiplied by the overall cost, which is there per item. If items are defective, every lot will be submitted for 100% inspection, and the amount of inspection per lot would be the lot size capital N, because now you are basically actually inspecting each and every item. So, in the initial case, you have a so called lot in front of you, which is capital N. From there you pick up small n and you make a decision. But now if you have to do inspection for each and every lot, so obviously the lot total cost would be the cost of inspection multiplied by the number of items which are there in the lot, because as you are doing 100% inspection. If the lot quality, the average amount of inspection per lot will be basically be there between the sample size n and lot size, which is obviously true, because if you pick up a sample size and if you want to do full inspection, or in one case you want to do some intermediate steps, so the number of inspection would definitely be in between a value of small n and capital N. If the lot is of quality P and the probability of acceptance is given by PA, then the average total inspection per lot would be given simply by this. So, what you do is that you picked up a lot, so that entails a cost, and also you will basically be doing a total cost structure for the values, which are two things we should remember, is that what is the amount of such objects which are there, which are being accepted or rejected. So, those would be what. So, if you pick up a small n, the rest left is capital N minus 1. So, obviously there would be an overall probability of cost based on the fact that those capital N minus small n are being left out. So, that would technically be multiplied by 1 minus PA, because PA we know is basically the acceptance probability of a lot depending on what is the overall numbers of the values of capital N, small n and C. Now, the average total inspection. So, just I thought I will mention you the examples which would be there for either the problem or when you are trying to read the book, though would be quite exhaustive from the point of the book. The book covers a huge amount of concept and absolutely very nicely done. But the examples which we will consider for this TQM would be based on the slides only, and they would be a little bit more conceptual without going to the nitty-gritties that how those problems have been solved from the textbook sort of point of view. So, the average total inspection ATI is basically being measured along the y-axis, and the lot fraction defective, as we have been doing for the OC curves, are being measured along the x-axis, and as the capital N value changes, obviously small n changes, C changes. So, keeping small n and C fixed, you will basically have different curves as shown in the plot. Now, the question is that as capital N is changing, small n is changing and C is changing, obviously you will have different scenarios enacted in front of you. So, that you have to be careful in order to understand how the total the average total inspection or the ATI would basically look like depending on the change of capital N, change of small n and change of C. So, this figure 15.12 gives you the average total inspection for the curves, given the fact that small n is 89, C is 2, for lot sizes depending on how you have taken them. So, the lot sizes in one case is 5000, another case is 1000, another case is basically 10,000. Accepted sampling, basically the important points are the AQL level is the percentage of defective items a customer is willing to accept from you, a property of manufacturing process, which is basically a sort of error. So, as I mentioned, these are basically alpha and beta errors which you also encounter in hypothesis testing. Lot tolerance percent in defective, which is the LTPT, is the upper limit on the percentage of defect a customer is willing to accept, which is basically also would have a consequence or the information based on the alpha and beta value. The average outgoing quality AOQ is the average of rejected lots and accepted lots, and similarly you have basically AOQL and ATI, which gives you the maximum AOQ value, which the peak happens for a range of fraction defectives as mentioned, and the average number of units inspected per lot would be given by the concept of ATI. Now you have to basically design a sampling plan, and we will very simply consider it the single sampling plan only. We won't be going to the complications of double sampling plan, sequential sampling plan and all these things. So operationally 3 values need to be determined before a sampling plan can be implemented, and as if you remember I have kept mentioning the concept of capital N, small n and C repeatedly. So these as you see are turning out to be the important factor based on which you can find out and design the sampling plan. So capital N is the lot size, the number of units in the total lot which you want to actually inspect, given time and money are not an issue. Small n is the sample size, the number of units in the sample which you pick up from that lot, and C is the accepted numbers for that particular lot depending on the value of n which you have. So obviously the ratio or the probability of defects which you have from the overall lot would also have some implications. What is the value of C for the sample which you are going to pick up to test that lot. While there is not no straightforward way of determining these values directly, given below are the desired values of the parameters and the tables have been developed accordingly. So basically it gives you 4 columns. In column 1 is basically the value of C, if you remember the number of defects. Another value you have basically is the ratio of LTPD and AOQL. So AQL. So obviously you can have 2 different columns also to find out the LTPD and AQL values, which are technically gives you some information about the alpha and beta or the producer risk and the consumer risk. You have N, which technically is the AQL value, and you have basically the for those values of N you have basically the LTPD value. Now only important thing is to remember is basically on the second column you are trying to measure the ratio of the LTPD and AQL value, based on which you will take a decision accordingly. So as C changes from 0 to 9, these values are LTPD to AQL or on a single column, which is the third one and the fourth one, you have the AQL and the LTPD values as noted down. Now I have been mentioning, if you remember, the word alpha beta time and again. So let us come back to this concept again. So 3 alternatives for specifying the sample plans are the producer's risk, which is basically 1 minus alpha or the AQL specified values, the consumer risk, which is beta, which is the LTPD value, and all the 4 parameters need to be specified. 4 parameters are, if you remember, capital N, small n, C and D. So in this example, given a producer's risk of 0.05 and the AQL value of 0.1015, you want to find out or determine the sampling plan. So from the tables and the informations you will have, as C is 1, the N value will be calculated depending on the ratio of the values of AQL and LTPD, which you already mentioned. From there you go down the table, find out the C value, and then go horizontal to find out the values of AQL and the LTPD values, from where you can find it out. So for that you find out the N value coming out to be one case about 24. That means for the whole lot you will pick up a sample of 24, given that C value is 1. In case C is 4, then you have to basically find out the value of N, which comes out for the lot as 131. And for the second example, given a consumer risk, so initially it was the producer risk, now it is the consumer risk, and the LTPD value of 0.08, we need to determine the sampling plan. Again you use the same formula, find out the values of N as the ratios, and those values comes out to be 29 and 116 depending on the value of C as 0 and 5. In example C, given producer risk of 0.05, consumers risk of 0.1 and LTPD of 4.5 and the AQ value of 1%, we want to find out what is the sampling plan. Again you use the formulas which are given, and you can find out the values of N accordingly. So here I am going a little bit fast, but trust me, if you go through the slides, read the books, the overall general plan of how you solve the problems would be clear. Another thing which you may be finding in last 3 or 4 lectures, I am going a little bit fast because the reason is that total quality management is a very vast subject, very interesting subject. So, rather than basically spoon feeding you, I would basically try to encourage you to read the topic, understand the slides, ask questions, and try to understand the concept of quality control or total quality management or the quality control process tools or the mathematics based on which the overall philosophy of quality works. Now, till now we have been considering the single sampling plan only, that means pick up only test that and basically accept or reject. Now, in the second stage, before the sequential sampling plan comes, we have the double sampling plan in an effort to reduce the amount of inspection or double or multiple whatever it is. We basically do a sampling where we pick up a set of observation for the first sample which is given as N1, inspect it. If that is given as C1 and if D1 is less than C1, you basically accept it. If D1 is greater than C1, you reject it. But there may be some instances that the values of D would be between some specified limit. So, typically the 4 parameters based on which we will try to do the studies, obviously D1 and D2 are the number of defects which are happening in the first sample and in the second sample, depending on how you have picked up the observations from the lot capital N. N1 is the number of units in the first sample and the acceptance number in the first sample is corresponding number is C1. N2 is the number of units in the second sample and the corresponding acceptance number of both the ones is given as C2. So, obviously, the acceptance number in the second lot would be C2 minus C1. So, the distinctions can be made accordingly, where you can only specify the number of defects in each lot, or you can basically say the number of defects or allowable in the second lot when you already picked up the first lot would be C2, where C2 would be the sum of the number of defects you are getting in the first picking and the second picking. If you do it in the third case, if you have C3, then C3 would be the sum of all the defects which you are getting in stage 1, stage 2 and stage 3. So, advantages of double sampling plans over single sampling is that it may reduce, which you do not know, but technically in sequential sampling plan where you go in different multi-stages methodologies, the total amount of required for inspection is low, which would basically have a positive effect on the total cost structure. Suppose first sample in a double sampling plan is smaller than for the single sampling plan. So, obviously, it would mean that overall cost structure is being affected, but obviously that may compromise on the overall total quality. So, if lot is accepted or rejected on the first sample, cost of inspection is lower. Also possible to reject a lot without completing the inspection for the second sampling may be there. So, double sampling plan is basically what I mentioned in words, comes out like this. A double sampling plan proceeds as follows. So, in the first step, a random sample of size N1 is drawn from the lot. If the number of defects which is D1 for the first lot is less than equals to C1, the lot is accepted. In case, say for example, D2 is greater than C2, then obviously the lot is rejected. C2 is basically the total sum of defects which you will have in the two picking which you are doing. Now, if neither of these conditions are satisfied, obviously because C2 is greater than C1, so in case when we pick up D1, D1 values may be greater than C1, but less than C2. So, then what do? If neither of these conditions are satisfied, a second sample of size N2 is drawn from the lot. If the number of defects in the combined sample, which is D1 and D2, is greater than C2, it is rejected. If not, the lot is accepted. But in many of the cases, it may be possible that the sum of D1 and D2, if they are less than C2, then some decisions has to be taken accordingly. So, as given in this figure 15.13, again taken from Montgomery, is inspect a random sample of size N1 from the lot. Is D1 is the number of defects, and have some value of C1 and C2 already specified. So, if you look into this curves or the flow process, the operation of the double sampling plan is for this case given as N1 is 50, C1 is 1. That means out of this N, if you find out N1 50 as defects as 1, and if they are less than that, you accept that. If they are more than that, and in the single sampling, you would have rejected that. But now you are not doing because you are going for the double sampling plan. Then in the second lot, you pick up N2 observations from the capital N, and now the total number of defects is 3. That means there is a probability of getting 2, not the probability, the overall number of defects in the second lot is now 2. Now, if with this information we see the flow process, it basically works in this way. You pick up on a set of observation which is N1 from the lot and try to count the number of defects. So, if the number of defects is less than C1, which is 1, you immediately accept that lot. Now, if it is greater than 3, you reject that lot, but there may be instances where D1 is basically between C1 and C2, which is basically between 1 and 3. So, this is what is mentioned at that level where I am pointing my fingers, or let me make it more explicit, where I am basically circling this. So, if D1 is between C1 and 3, so you basically inspect the second sample of 100 observations from that lot. If D2 is the number of defects which have been observed, and then what you do is that find out the sum of D1 and D2. If D1 and D2 is greater than C1, C2, you basically reject that lot. If it is less than equal to 3, you basically accept that lot. So, in this sequence you can go from stage 1 to stage 2, stage 2 to stage 3. Say for example, you have the triple sampling plan, and there you basically have the sample size N1, N2 and N3. D1, D2, D3 of the number of defects you will get in the first picking, in the second picking and the third picking, and consider C1, C2, C3 are the numbers, which means that C1 is the number of defects which is allowable in first picking, C2 is the total number of defects which is allowed by the sum of C1 and the second stage pickings which you are getting, and similarly in that case you will have C3, which will basically mean the total number of defects combined, which is C2 plus the number of defects we are going to get in the third sample, would be equal to C3. So, obviously your sequence of movements of the flow process would be tempered accordingly or made accordingly. So, the double sampling plan operating characteristic curve, the triple sampling OC curves would also be dictated according to the values of capital N, small n1, small n2, C1 and C2 for the case of double sampling. In case if it is triple sampling, the OC curves would be dictated by these values, which are small n1, small n2, small n3, capital N. Then the other values which will dictate the OC curves, how they look like, shape and size, would be basically C1, C2 and C3. So, again we are measuring the probability of acceptance PA along the y-axis, lot fraction defect along the x-axis, and the probabilities of acceptance depending on the level of these values which I just mentioned. So, capital N, different combinations of ni's means I can be 1 for single sampling, can be 1 and 2 for double sampling, can be 1, 2, 3 for triple sampling. So, the probabilities of rejecting of the first sample is given on the right hand scale. So, they are given on the y-axis, where I am pointing my palm. So, then the probability of acceptance of the combined cases are given in the left scale, and based on the combinations you proceed to find out that how the lot size inspections would be done based on the algorithm which you have already discussed. So, OC curves for the double samplings for one example is given, where you measure PA again also along the y-axis, P along the x-axis, and then the first stage or the second stage probabilities are given on the right hand side. So, in one case you have basically the OC curves when you have done the first level, then another case would be the combinations of the first and level. So, based on that you will have different values of producer risk and consumer risk, and you can proceed accordingly to find out what is the total cost of defects which are being accepted or the number of good items which are being rejected. So, OC curve calculations depending on the binomial distribution. I am mentioning the word binomial distribution because either you accept or reject that particular lot which is there in front of you. So, N1 values is 50, C1 as you remember is 1, N2 is 100, N3 is C2 is 3. So, if P suffix A denotes the probability of acceptance on the combined scale, and P stage 1 suffix A and P stage 2 suffix A denote the probability of acceptance on the first and the second sample, obviously it will mean the probability is basically sum of P suffix 1 suffix A plus P suffix 2 suffix A. So, based on that you basically find out. So, I should be using the word prefix of 1 and 2 rather than suffix, sorry for that. So, P's prefix 1 suffix a is just the probability that you will observe that D1 is less than equal to C1, which is D. That means because in the first lot when you pick up, you are already specified that C1 should be the number of defects, but if D1 is less than C1, obviously you will accept that lot. So, out of a sample observations of 50, which is given by N1, and based on that you basically find out the probabilities, so sum of the probabilities. So, now the sum of the probabilities D1 can be either 0 or 1. So, if C1 is basically 2, the D1 values can be the 0, 1, 2. So, obviously you have to add them accordingly. Then in the first lot again is a binomial case, because you had basically N as 50, which is the total sample size, and then the number of defects and non-defects would basically be either D, which is the effective one, and the non-defective one would be 50 minus D1, because 50 is the total sample size which you have in front of you. So, that would be multiplied, that would basically be the values based on which you will multiply the probabilities of P1 and 1 P and 1 minus P, which is the level of acceptance or rejections which you already have. Now, in case if a small p is given as 0.05, which is 5%, and that is given with the fraction of defective in the incoming lot, then you obviously put those values and find out the value comes out to be about 27.8, which is 28%. A second sample is drawn. Again, if D1 is between C1 and and C2, then obviously you will basically accept it. In case if, say for example, D1 plus D2 is more than C2, you will reject it. So, a second sample is drawn only if there are 2 or 3 defects on the first sample, and that depending on how the example has been formulated based on the values of small n1, small n2, capital N, small c1, small c2, small d1 and d2 would basically dictate what the values are. So, calculations would be done accordingly. I will just go through the steps in general. I will again illustrate that later on in the class following that. So, D1 is given by 2 and D2 is given, D2 can be either be 0 and 1. So, if D1 is 2, obviously it would mean that in the total combination is basically C2, which is already fixed. So, which means that D2 in the next D2, which is the number of defects in the next slot, would be 0 or 1, because 0 means this value of D1 and D2 is less than equal to 3. So, this is fine, we will accept that, or basically consider that as a good lot. In case, say for example, D2 is 1, still 2 plus 1 is 3, which is less than equal to the value of C2 which we have, and we will basically accept that particular lot. But in case, say for example, D2 is 2 and more, then the sum of D1 and D2 is more than C2, obviously we will reject that. So, with that concept, let us proceed. So, D1 is 2 and D2 is 0 or 1, that is we find 2 defects in the first sample and 1 or less in the defect in the second sample, then the probability would be found accordingly. So, this would be a multiplication of probability, because they are independent of each other. So, what we find in the first lot would basically definitely have a consequence on the decision, but the calculations would be independent, because the probability of one lot does not affect the probability of the second lot and vice versa. So, you find out the probabilities. So, the probabilities in one case would be that you have already 50, remember is N1, based on that you find out, because D1 is specified at 2, so that number is fixed. So, once this number is fixed, this calculation of this is not a summation, is basically a fixed value, because this 50 is the total size N1, 2 is the value of D1 which you have, and based on the probabilities of the values which is already given as 0.05 and 1 minus 0.05, which is 95%, we found out these values. In the second stage we sum up. So, summing up are done for what values? They are done for D2 is equal to 0 and D2 is equal to 1. So, if we see the limits in this notation, so this D2 basically changes from D2 1 as specified, and from that you find out the probability comes out to be about 0.97%. In case D1 is 3 and D2 is 0, obviously in that case, because you have already specified C2 as 3, so in that case if you have, again you find out the probabilities, multiply them because they are independent. Once you find out the multiplication of those values, it comes out to be 0.01, which is about 1%, about 0.01, yes. Thus, the probabilities now in the second stage would be, in this case, a combination. In the first case, you have a combination of, say for example, D1S2 and D2 is less than equal to 1. So, and in the other case, you will basically have D1S3 and other case obviously D2 would be 0, because you already picked up all the bad items accordingly. So, if you calculate the values, the probability comes out to be about 0.29% value, as in the probability sense. In the percentage sense, it will be about 29%. So, I will go through these problems once again, and the problem set would be considered accordingly. So, have some patience, go through the book. I am sure you will understand. The problem set and the concept are very huge, but once you start reading, you will definitely get a hang of the picture accordingly. And we are open to suggestions, open to queries, and please get in touch with us for whatever queries you may have. Have a nice day. Thank you very much.